Okay, so we're very glad to have Dionysios, who's recently joined King's College. So Dionysios is one of the 2 experts in the world on de Sitter space, and he's going to tell us about this very mysterious and interesting topic. So there'll be 3 lectures today, tomorrow, and on Thursday. And okay, so thank you very much, Dio, for coming and for telling us about this.
Yeah, I'm very happy to be here. And very inspired to be here. I love this campus. And I have to already there was already a mistake in the lecture because there are no experts in this subject. And I think that's an important point to emphasize, given the motivation I will give in a second. Okay? Well, I don't know how far we'll get because I'd like to sort of present the material at a pace that's reasonable. But here's a rough sketch of what kind of things we might cover along the way. So my goal is to give an overview of a subject that I find very interesting. And the reason I find interesting, which is the motivation of why I'm giving this subject, has to do with experiments, actually. And it has to do with 2 experiments that were very surprising that happened within the last 20 years. Okay, so this is recent knowledge about our universe that I'm talking about. And one experiment had to do with an observation of relatively recent light coming from the explosion of supernova everywhere in every angle in the sky. And what was observed was a redshift that was related to how far the explosion occurred. And the simplest interpretation of this data that came from observing the spectra of supernova explosions in the sky was that our current universe requires a term in its Lagrangian that is a cosmological constant that causes space to expand, and not just expand, but expanding in an accelerating fashion. Okay? So by studying the light of distant exploding stars, we seem to conclude that we're currently living in a phase that's entering more and more exponential expanding phase. So that's today. There is also some other light that we studied when looking at the sky. And this light is older, much older light. And it comes from the cosmic microwave background radiation. And this light, to first approximation, looks like a perfect thermal spectrum at around 2.7 Kelvin. However, upon more careful observation, it was noted that this is not a perfect thermal spectrum, but rather it has small jitters of the order of 10 to the minus 5 in units of the original temperature. And these jitters are interesting in and of themselves. However, the true surprise came when it was observed that these jitters weren't just random noise, but rather they were noise that had a structure. And this structure was scale invariant. Okay? So studying 2 types of cosmic light led to in the case of the supernova, a conclusion that we're currently expanding. And in the case of the cosmic background light, which came from the past, the suggestion is that even the early phase of the universe was expanding, albeit at a much faster rate. So it seems that to think about the early structure and late-time structure of our universe, we may have to confront the question of exponentially expanding space-times. Okay? So my motivation is related to these experimental results. But of course, I'm a theorist. I haven't done these experiments myself. And there's a theoretical motivation behind why I want to talk about these things, which also is due to progress that happened in the last 20 years. rather remarkably, the coincidence in time between the birth of ADS-CFT and the observation of positive lambda and scale-invariant fluctuations are roughly of the same order in time. Now, the theoretical motivation in one sense or another is the idea that even though Einstein's theory of general relativity is formulated in terms of a metric variable as a geometric theory, the suspicion is, with strong evidence in the case of universes filled with a negative cosmological constant, that ultimately the metric field is itself an approximate notion, something that emerges in a limit and makes sense only in that limit and must be replaced by different, more fundamental degrees of freedom away from that limit. And an analogy, an imperfect but somewhat good analogy, is the relation between the theory of molecules and the Navier-Stokes equation. Okay, an analogy that's very that was developed very nicely actually over here in India. But the suspicion is not that this is just true for anti-de Sitter universes. The suspicion is that this is true for space-time in general. And in other words, the suspicion is that it might also be true for whatever space-time fills our own universe. Okay? So this is after 20 years of thinking about the ADS-CFT story, our suspicion is that this may well be a general notion of space-time. And so perhaps it's time to try to merge these two ideas, one from the theory world in the last 20 years, one from the experiment world, and try to see how far we can get. This is roughly the motivation of the subject. And you may think that it's a little academic to try to think about quantum gravity in de Sitter space. However, precisely because of when it happens, in the early universe, for example, we may have to confront the possibility that it happens at scales that are close to the string or the Planck scale, in which case quantum effects become important. And so understanding quantum effects in de Sitter is not some academic problem, but it may be intricately related to understanding the dynamics of the early universe and inflation, if that's the early universe. And for the second problem, there are infrared effects that we don't understand either. For instance, from the perspective of an observer sitting inside of an expanding universe, as we'll discuss a little later, one observes a horizon. And so even though we're talking about an essentially time-dependent type of space-time, we're confronted with questions very similar to those of black holes, which are horizons. And so even in the current phase of the expanding universe, there are quantum effects, perhaps related to the entropy associated with this horizon or other features, that we have to confront again. And so my suspicion is that it's not just an academic game to understand quantum effects in the de Sitter universe, but rather an intimate piece of the puzzle of our own space-time. Okay? So I hope with that I've sort of justified the existence of these lectures, even though this is a very much open problem with waiting for experts in the making. Okay. So that's my motivation, but are there any questions? It's always good that there are no questions during the motivation phase, because there are going to come a lot of questions now. Okay, so the goal of the lectures, having given my motivation, I just want to go through some early basic facts about the geometry, the idealized version of the geometry where we assume it's an empty, pure, eternal de Sitter universe. We will talk about fields, how they behave in this universe, how they behave differently than fields in flat space, for example, or more familiar situations. Then we'll turn on a very small h-bar parameter and try to understand little quantum aspects of these fields and see what they look like. We'll study some features of the symmetries, the unitary representations of the symmetries. And finally, we'll discuss some speculations that people have talked about in the context of a broader proposal for quantum gravity in expanding spacetimes. And this will come in two flavors. I don't know how far I'll get. I will consider this a success if we get up to here, okay? And then afterwards, when we go downtown to Bangalore, we can talk about these things, but we'll see how far we get. And I'm here all the week, so okay, so let's start with the most basic aspect, which is, I'm going to describe the geometry that we will be interested in the classical limit. So this is a maximally symmetric solution to Einstein's equations with a positive cosmological constant, okay? And what I'm presenting now is a chart that covers the full space-time manifold. It's a global chart where the coordinate t ranges from -π/2 to π/2. And this object over here is the unit round metric on the 3-sphere. Okay? And this is known as the global chart of a de Sitter universe. Can you read back there? Yes? Okay. So, so let's think about this geometry a little bit, and I'll try to engage you in some back and forth. Are there any manifest symmetries that you can see in this geometry? Any takers? I'm doing this partly to raise the adrenaline so that we're all paying attention. But are there any symmetries that you can see? So let me answer the question. So one manifest symmetry over here is SO4, which corresponds to the rotations of the 3-sphere itself. Okay? There are other more subtle symmetries, such as discrete transformations of t to -t. But the one I want to emphasize from this coordinatization is the SO4 symmetry. And the other thing you'll notice is that I've written the coordinate system in a conformal way, and you'll notice that the geometry is conformally equivalent to what's known as the Einstein static universe, which is a product of a 3-sphere times time, okay, except that the time now lives on a finite interval. And so we can draw a Penrose diagram, for those of you who are more geometrically inclined, to describe the causal structure of the space-time. And the way to understand this diagram is, well, null. So 45-degree lines are null directions. And this over here is a complete spatial slice, so it corresponds to a 3-sphere. To a full 3-sphere. The poles of the 3-sphere lie at the ends, for example. A point on this line is a 2-sphere, and the 2-sphere grows from one pole until a maximal size in the center and then shrinks again. Okay? And finally, time is going forward, and there are two singular points in the geometry, namely the infinite far past and the infinite far future. And the proper size of the 3-sphere is infinite at both of these singular points. So we have a sphere that's infinitely large and shrinks to some finite size and then grows again. And all of this geometry depends on a length scale, which I've extracted out of the coordinates and put in front of the whole metric, L. And today's value of L is 20 billion light years or so. And we do not know the value of L during the inflationary picture of cosmology. It could range dramatically from the TeV scale up to the Planck scale. It's one of the unknown parameters of the theory. Okay? Now, so I wanted to show you the global structure of the geometry. However, the piece of the geometry that is most relevant to observation is actually the expanding part of the geometry. We have no evidence for this piece of the geometry over here, right? Because we only observe the expanding phase of this geometry, and there's a particularly convenient coordinate system for the expanding phase, which I'll now describe. And I'm writing all these coordinate systems because eventually I want us to derive the symmetry group of de Sitter itself. And so it's a fun exercise to do that by considering different charts. So one way to reach this metric is to take a limit of this metric where t approaches π/2. So So if you take t to limit to pi over 2, and then you rescale the coordinates of the three spheres so that it essentially decompactifies, you end up with a coordinate system where the spatial slices are planar. Okay, so this over here is the standard metric on R3. And eta over here is a coordinate that ranges from -infinity to 0, a forward conformal clock that ranges from -infinity to 0. And and this is the kind of coordinate system that cosmologists like to use because they like to use a Fourier analysis on R3. Okay? Now, what piece of the full Penrose diagram is covered by this coordinate system? Any takers? Okay, so let me give you the answer. It covers either the top half or the bottom half, okay, of the coordinate system, where this null line over here is the limit of eta going to -infinity, and this line over here is the limit of eta going to 0. Okay, and the spatial slice on this geometry corresponds to such lines over here. So those are surfaces where eta is constant. Okay? So now let's play our symmetry game again. And this time I'm going to wait until someone gives me an answer. Yeah. 0 minus, thank you. 0 is to be understood as 0 coming from, what did I write, 0 plus? Well, good, very good, thank you. Yes, eta is always negative. It approaches 0 from the negative side, thank you. Okay, so now we're going to play this game and see if there are any other symmetries we can extract out of this geometry. Any other manifest symmetries that we can try to read off. Sorry? Okay, a far less trivial symmetry than SO4, yet somehow one that we're all familiar with. I suspect I know the reason why. It's because we've studied ADS so much that we know it. But indeed, there's a symmetry which is given by rescaling by a positive number lambda, eta, at every point, and also not just the clock, but the ruler as well. So if we rescale our clocks and rulers concurrently at every point, our metric remains invariant. And indeed, this is a symmetry, a non-compact symmetry, which we can call SO1, since you all identified it with a dilatation. And there's another manifest symmetry, the one I thought we would get first, which is the translations and rotations on R3. And this one is the Euclidean group, ISO3. Okay? And so, okay, so I want you to get a feel for the geometry now, because we're going to try to guess the full symmetry group of this metric. And it's going to be interesting. So it has to have as subgroups, so it's going to be finite, a finite dimension, a finite number of generators. It's going to have SO1, ISO3, and SO4 as subgroups. And so can anyone guess what the isometry group might be of this geometry? And then we'll discuss why it's surprising. Any wild guesses? Mistakes are a good thing in physics. Okay, it's an unfair, maybe it's an unfairly hard question. But so let me write down the symmetries. Fully. And then we can try to describe some properties of the symmetry group, because the symmetry group turns out to be rather important. Right. So hopefully I'm not making mistakes over here, but I'll have to check with my notes. Let's see, b has units of 1 over x, and so we need an x squared here. Okay. So the following, if one does the calculation, can be shown to be isometries of the Poincaré system. And so let's now count the number of parameters that we have in our symmetries. We have one parameter associated to the scaling invariance. We have 3 rotations on R3 plus 3 translations, so that gives 7. And then we have B over here, which is, sorry, these are part of the same isometry. And then we have B, which is another 3 vector, and so we have 1 plus 3 plus 3 plus 3 gives 10. So I've given you another piece of information, which is that there are 10 generators in this group, which has an SO4 subgroup, an SO1, 1 subgroup, and an ISO3 subgroup. And now we can sort of reconstruct the answer. The answer is the symmetry group of the Sitter universe is the SO4, 1 group of Euclidean conformal transformations. So let me now talk a little bit about this group simply at a classical level, and then when we discuss some aspects of quantum fields, we will discuss what's known about the representations of this group. But let's first just talk about some basic features of this group. So, and I'm going to put Euclidean in quotation marks because, of course, this is the symmetry group of a Lorentzian spacetime. And so we have to be careful about what we mean by the word Euclidean here. So, first of all, are people familiar with this group? SO4, 1? It is the same group. Okay, so good. So this is not some random mathematical object. It's a group that appears in nature all over the place. And I'll give you another system where this symmetry group appears, and that's the 3D Ising model at the critical point. And also, if you tune the pressure and temperature of water to its second order phase transition, there's a critical point that's supposed to be described by the same critical point as the 3D Ising model. And so the symmetry group of boiling water at a special pressure and the symmetry group of a cosmology are the same. Okay, so this is quite remarkable. It's a group that we're accustomed to seeing when studying critical statistical systems, where the word Euclidean is appropriate, because there we're dealing with timeless systems and their critical fluctuations. Okay, and now we're seeing this same group appearing in a totally different context due to the particular dynamics of a cosmological type of spacetime. Okay, so this symmetry group is nothing too far from reality. It's just a symmetry group of the 3D Ising model. Okay? And any questions about that? What's surprising about the group in this context is that it's, as I said before, not the group of a statistical, timeless Euclidean system, like a bunch of spins and where we sum over different configurations weighted by some weighting factor, Boltzmann factor, whatever, and we study the critical fluctuations of that system. Here it's a group that is intimately related to the dynamics in time. Okay? And this, the reason I emphasize this is that in a lot of the literature this has been a point of confusion about in what sense the group of de Sitter motion in de Sitter is a Euclidean group and in what sense it's a Lorentzian group. The reason it looks Euclidean is that we no longer have a time-like global killing vector in the space-time. So there's no piece of the group that globally describes evolution in time, okay? Nor eta, nor t, nor any translations that push you forward in time are globally time-like. There is no globally time-like killing vector in this geometry, And so there's no piece of this group that we could extract and talk about its translations in time. Instead, it's replaced by something like your scale invariance or something else. And the other reason that it looks Euclidean is that if we study the action of the group at very late times, okay, so we take the limit to 0 minus of eta and look at the group acts in a very simple way on the pure metric at the future boundary, which is the flat metric R3. It acts, it basically maps the metric on R3 to itself up to a local conformal factor. And so these are it's the conformal group of the metric on R3. Okay, and you can see this because if I switch off eta over here, well, these two are straightforward, but these over here, people will recognize if they've read the big yellow book as the standard special conformal transformations on R3. And if you do the exercise and act on R3 with these coordinates, you'll get the flat metric on R3 up to a conformal factor. In other words, they constitute conformal killing vectors of R3. And in that sense, it is an essentially Euclidean structure. Okay? But we mustn't forget that we took a limit to isolate that essentially Euclidean structure, which was the late time limit. Okay? And so I would like us to bear this in mind throughout the remainder of the lectures. Okay. So now what we're going to do, wow. I'm still old. I still read. Okay, so now what we're going to do okay, so we've understood the background a little bit. We've understood the stage, and now we're going to put some actors on the stage. In other words, we're going to do the most simple, straightforward thing. We're going to study the motion of a classical field propagating on a fixed de Sitter background and see its behavior. I always have, at this point, I have a little bit of a concern with the timing, because I would like to tell you one more feature about the geometry, which is something about the horizon. But if I do that, I'm worried that it'll distract the discussion. So keep in mind, and under all circumstances, I must, please remind me at the very end, if we don't get there, to talk about the de Sitter horizon for at least 5 minutes, okay? Because I think it's essential to the problem. I don't do it because I'm doing a symmetry-based approach now, and the symmetries are not very manifest from that perspective, okay? But physics-wise, I think that's a very important piece. Okay. De Sitter. We're not allowed to say ADS. Yeah. But I guess symmetries are also like you can actually find the killing. Yes, but I didn't want to do that exercise on the blackboard because it's a somewhat technical exercise. I mean, of course, you can solve the killing equation, and it's the same answer. I just wanted to give a discussion where we see the metric and start feeling out so that we can become engaged with the geometry. Of course, this is. And in fact, where there are more direct ways to see it as well, where you view de Sitter as a hyperbola embedded in a high-dimensional Minkowski space, and these are also the Lorentz symmetries of a high-dimensional space. But somehow I feel that puts an emphasis on certain technical aspects that are not related to the space-time itself. I'd like to focus on the clocks and the rulers and the... Okay, but yes. Okay, so what we're going to do is the simplest thing, which is we're going to study the behavior of a scalar field in a fixed de Sitter background, and we'll already see some surprises. Now, once again, remarkably, this simple exercise is not just an academic tool, because if the early phase of the universe is described by an inflating space-time, there is a scalar particle in all those models, which is the inflaton, and to leading order, in some approximation, its dynamics are governed precisely by this equation. So it's a fun exercise to do, and we don't need to feel that it's too much of an idealization. But I'd like to treat it as if it was an idealization now. Okay, so, and moreover, we're going to discuss things in the planar coordinate system. So we're going to, because the symmetries become a little simpler. So let's do that. And so, yeah. Do I have it wrong? Yeah, I might get a, yeah, okay. Okay. Okay, so let's see. So this over here, so G inverse is eta squared, eta 1 over eta to the 4, so that's another 1 over eta squared. Good, okay. And then the root g's cancel, we get an eta squared. And then we get, so I'm purposefully doing this in real time because it makes me go slower and we can all do the calculation at the same time. And by the way, here I'm parameterizing the calculation in terms of a dimensionless number that's natural to the problem, which is the mass of the particle measured in units of the de Sitter length scale. Okay? That's this product of mu times L. And the equation we need to solve is the following. Now, this is a partial differential equation that's complicated because phi is a function of both eta and x, but we're going to take advantage of the observation that it seems certain things simplify in the limit eta goes to 0 and try to solve the equation in that limit first and see how it behaves, and then I will just tell you the full solution. Okay? And I'm going to make an assumption here that in the limit eta goes to 0, this piece of the equation and this piece of the equation are more singular than this piece of the equation. If you want, we can first make that assumption by assuming that the spatial profile of the field will be mild enough that I can isolate that point, but we'll see that that's effectively guaranteed in taking that limit. Now, a word on coordinates, another word on rulers. I don't want you at any point to confuse the coordinate x with the physical length. Separations in x are coordinate separations, and one must always keep in mind that eta weighs the proper length, okay? And so a small distance in delta x may mean something very large physically if eta is small enough, okay? So please keep in mind the difference between proper distances and coordinate distances. It's another thing that is peppered with confusion in discussions of this subject. Okay, having said that, let us assume now, and then we'll check that it's a self-consistent assumption, that this term is subleading, less singular than the remaining terms. And what this means effectively is that our problem becomes not a partial differential equation, but rather an ordinary differential equation. And ordinary differential equations we can do. And now we'll test whether Suvrat's sign was right or wrong. So now we are confronted with the problem of solving the following ordinary differential equation. And I'd like someone to propose an ansatz for this ordinary differential equation. The ansatz should be motivated by the symmetry that we keep on exploiting. So whoever suggested that there's a dilatation group may want to suggest an ansatz as well. 7 more seconds. Eta to some power? Oh, fantastic. So we're going to use this ansatz. So we're going to use the ansatz, which is that let's assume eta is, let's use the notation of the proposed ansatz, is some, Okay, but this notation makes it confusing for me. Let me give me your second favorite letter. Kappa, thank you. Okay. Okay. So we're going to assume that the following ansatz is a good ansatz. And since we said that we end up with an ODE, we can multiply this power of eta by any arbitrary function of the coordinate x. Okay? Now, let's do the calculation. The calculation gives us, okay, we bring down a power of kappa. And then we multiply, so we have kappa minus 1, kappa minus 3. And when we bring down another power of kappa, minus 3, and then we have a minus sign. And we end up with the following algebraic equations. In other words, the ansatz transforms the ordinary differential equation into an algebraic equation. And the algebraic equation can be solved in a straightforward manner. And the solutions of the algebraic equation, oh, by the way, I'm working in 4 dimensions. We're essentially going to be in 4 dimensions with no apology throughout the rest of the lectures. So the two solutions, right? It is a second order differential equation, so there ought to be 2 solutions. Indeed, there are. And the solutions look as follows. And so now we can write our general solution and we will describe some of its features. Okay? So our solution now for the late time classical dynamics of a free field in a fixed de Sitter background are given by the following. Okay? And now we're going to analyze this equation, this solution, in different regimes. And we'll see, okay, so let me first describe that, and then we'll see how these different regimes, when we do a small quantization of the field, correspond to an interesting property of the reducible representations, the unitary reducible representations of the Euclidean conformal group. Okay. So first things first. What happens when the particle is very massive in units of the de Sitter length scale? So regime number 1, very heavy particle moving in de Sitter. Now, intuitively, we can think of this regime as the regime in which the particle is not sensing, to a large extent, the fact that the space it's moving in is curved. Right? This is the heavy particle regime. And in this particle, kappa, okay, acquires an interesting feature. And the feature is that it acquires an imaginary part. It becomes a complex number. And the physical meaning of this complex number is that even at arbitrarily late times, the motion of the particle retains a standard oscillatory behavior that is mimicking flat space, e to the IMT flat space, oscillation with respect to time. So a heavy enough particle in de Sitter retains an oscillatory quality for late enough times. And this is the standard intuitive thing to make contact with. So oftentimes in the literature, one will see confusing remarks relating to the complexity of these numbers. In fact, it's nothing but the opposite. When these numbers are complex, you are making contact with the most standard physics that we're accustomed to, okay? Because that's when eta has a power with an imaginary part. But remember, the proper clock is the eta over eta, which is e to the t. And so really, it's an oscillation in terms of the proper clock of the particle, okay? So the mystery of the I, of the complex kappa, is nothing more than standard oscillating particle motion, okay? So that's the heavy regime. And we'll make contact, as I said, in due time we'll make contact with this from the perspective of a quantum field in de Sitter rather than a classical field. But I think it's important to first clear up our mind about the classical features, okay? Now there's a special point, which is when mu squared L squared is equal to 3 halves, And what's special about this point is that precisely for this value of the mass, which is not massless, okay, it's some mass, non-zero mass, this oscillatory behavior of the solution ceases to exist. And the nature of the solution space changes into two profiles that decay polynomially or exponentially in the proper clock at late enough times, okay? And there's another feature associated to this. Recall that the original field we were dealing with was real. And so if kappa was complex, it meant that our canonical data, alpha plus and alpha minus, which effectively can be viewed as coordinates in the classical phase space of the particle, had to be themselves complex in order to have a real solution. When the mass hits this special point of 3/2, alpha plus and alpha minus no longer need to be complex functions. They can be real functions, okay? And so there's a change also qualitatively in the description of the classical phase space of the classical field theory, okay? Of course, there had to be two, because phase space has to be even dimensional at every point x. Again, I'm emphasizing this to remind us that we're doing classical physics now. Sorry? There's a log? There's something singular. Sorry, yes. So let's stay slightly away from it. Yeah, that's true. So the two weights become degenerate at this point, and there's a logarithmic branch of the solution space. Thank you. Yes. I'm avoiding subtleties like that because I want to talk about the behavior of the field, but that's a good point. So oftentimes when the solution, there's a degenerate point in the solution space because kappa plus equals kappa minus, one has to take the difference of the two solutions in the limit and generate a logarithm as well. Okay, that's an important point. Now, so this we can call some sort of critical mass. And finally, there's a range is this readable? No? Where mu is between being massless and this critical value, okay, the whole finite range of masses, where this behavior continues, this decay of both modes, this disappearance essentially of the classical wave into the infinite volume of the future. And finally, a very special point is encountered exactly at the massless limit. And what happens at exactly the massless limit is that one of the two kappas vanishes. And what this means is that however late we take eta to be, there is a profile that remains imprinted. Now this is important because this peculiar dynamical feature is what's responsible for any chance of observing scaling invariant fluctuations from an early cosmological era. It's this change in dynamics as we tune the mass that's special to de Sitter, and we'll see the features of the de Sitter group that allows things to happen in de Sitter that we've never seen when studying fields, for example, in flat space. Sorry? Oh, 9/4, excuse me. Thank you. Yeah. Okay, so here we've sort of, you know, already even the classical problem, we start seeing a host of interesting different phenomena depending on the sort of the only knob in our problem, which is the mass of the particle in de Sitter units. Okay, so now let me make some remarks about some other particles, and then I'll move on. Well, maybe we should end with the classical physics now, because I don't want to rush too many subjects. And I think it's important to, once we've organized our thoughts classically, we'll get. So now let's talk briefly about a particle with spin 1, a photon, in a de Sitter background. And some of you may know that Maxwell's theory, free Maxwell's theory in 4 dimensions happens to have an interesting property, which is that it's conformal at the classical level. It's conformally invariant. But I told you before that as far as this metric is concerned, conformally, it's equivalent to flat space or the half space. And so studying a spin 1 particle in de Sitter is the same as studying a spin 1 particle in flat space as far as the solutions to the equations of motion are concerned. And so we don't expect any feature specific to de Sitter to dictate the dynamics of a photon traveling in de Sitter. Now, this is slightly unfortunate. What it means effectively is that the photon dilutes in an expanding space-time. So the energy density carried by the Maxwell field or any electric field dilutes, provided we don't make the electric coupling itself time-dependent. So this is a little unfortunate at a phenomenological level, because there's some hope that some of these very large magnetic fields observed between clusters of galaxies, so there's hints of very large magnetic field, intergalactic large magnetic field. People hope that these magnetic fields would be sourced by some electric field during inflation. But unfortunately, the dynamics of inflation doesn't quite allow for the production of these large magnetic fields unless one also does other things to the theory. Okay, so it could have been an interesting phenomenological feature, but unfortunately it's not. And finally, let's talk about spin 2. And I'm going to talk about massless spin 2 for obvious reasons, because that's the graviton. And so what I'm going to tell you now is the behavior of the solution of the linearized Einstein's equations about a fixed de Sitter background, and the behavior and late time behavior thereof. And so we're going to work in it. We have to fix a gauge to talk about this. And we're going to fix a gauge where the clock, something called the transverse synchronous gauge, where the clock and the eta x components of the metric are fixed to be 0. So the history of this gauge is interesting, I think. So we know it as the Pfefferman-Graham gauge, but I think the earliest paper with this gauge was a paper by Starobinsky in the context of inflation. I'm not sure about this, but he certainly wrote a paper very early where he fixed this gauge to analyze linear solutions. I'm not sure, though. I've been trying to dig up the earliest paper on this gauge. Anyways, it's a very useful gauge. And in this gauge, we can study fluctuations of the three metric. Okay, so we'll have H eta eta.
Did you say G eta eta, the fluctuations?
Oh yeah, just the full the 8 delta yeah. I'm just fixing. You can fix that gauge beyond just fluctuations for nonlinear solutions as well, for some finite amount of eta before the coordinate system breaks down. But as far as we're concerned, we can certainly do it at the linearized level. And the solution space organizes itself as follows. There are two branches to the solutions, which I'll call, these are analogous to what I called before are alpha plus and alpha minus. And one branch competes with the tree-level metric itself. So it has a 1 over eta squared. In other words, it's not diluted with respect to the background metric at late times. And this is important because any hope of observing something like a polarized tensor mode in the early inflationary era rests on the fact that the dynamics at late times of the spin 2 piece is not completely diluted, okay? And so, crucially, the linearized theory of a spin 2 massless field in de Sitter is not conformal, unlike a spin 1 field, okay? It's a happy fact. And this over here is the correction, the leading correction to the flat metric on R3. And of course, this gauge hasn't fixed the reparametrization invariant completely because we have purely tangential diffeomorphisms that we can still act with respect to. And those can allow us to fix, for example, this object over here to be transverse and traceless. But that's just a choice. We can choose that. It's just a choice. The important point is that this object over here, with respect to some killing diffeomorphism field, some vector field purely of X, generates an equivalent physically configuration. Okay? But the important point comes in counting the degrees of freedom. You see, this is a symmetric 3 by 3 tensor, but it's subject to, It's a symmetric 3 by 3 tensor, and so it's subject to 3 diffeomorphisms, which take its 6 components down to 3. However, there's one more diffeomorphism that's left, which is related to what I said earlier in the lecture, which is that there's a local Weil invariance as well. So it turns out that when you fix this Pfeffman-Graham gauge, I forgot to mention this, the residual gauge symmetry is not just tangential diffeomorphism, but also transformation that involves eta times some small function of x in addition to x and some small function of x. And in effect, what this does is it multiplies the 3 metric by a conformal factor. And so that's why we can fix the trace of delta G as well. And so finally, after taking into account the 4 residual diffeomorphisms, starting with 6 degrees of freedom, we end up with 2, which is the number of polarizations of a massive spin 2 particle in de Sitter space, just like in flat space. Okay? So 6 minus 3 minus 1, so these are sort of the Weil part, these are the tangential diffeomorphism part. And similarly, this piece over here, which was the other canonical momentum in the phase space of the spin 2 particle, you can view it like the extrinsic curvature, something related to the extrinsic curvature of the spin 2 particle with respect to sort of derivative in time itself. Okay, so like the momentum carried by the metric field, the classical metric field, is subject, just like this piece is subject to residual gauge transformations, this piece is subject to constraints. And the constraints on this canonical data are indeed the fact that it's transverse and traceless. So this isn't a choice, this is a constraint, one of the linearized constraints of the Einstein's equations, and it causes this piece of the field to be transverse and traceless. And again, these are 4 conditions on a 6-component object, and so our momentum at each point, just like our position at each point, our metric and its momentum have 2 degrees of freedom, even in even-dimensional phase space, and the dynamics of the field is therefore consistent. So before moving on to the quantum, the ever so slightly quantum world, let me mention some few things that are known about nonlinear geometric solutions of the Einstein's equations. There's some natural questions that arise already at the classical level. So one question you may ask from a more global perspective is, imagine that I do put some data, some Cauchy data. The problem's Cauchy complete if the Cauchy slices are compact, so there's no subtleties with respect to flux leaking out of the system. But imagine we put some deformed metric on top of scribe plus. And now we can ask, is there a smooth extension all the way up to scribe minus or not? And so there's some theorems known about this, classical GR theorems. These theorems, so the basic one is due to Friedrich, I believe, and the claim is that if the topology of scribe plus is spherical or the Ricci scalar is positive, then small but finite deformations of the boundary metric lead all the way down to square minus. In other words, there exists a finite neighborhood of solutions to classical Einstein's equations with positive lambda that allow for a description of a perturbed eternal de Sitter manifold, okay? It's not just an artifact of the linearized analysis, where one can readily show it using the equations of motion, the linear solutions. It's a feature that is preserved at the nonlinear level, and that's interesting. A very simple example that you may look, I think exists for us, like nice concrete examples are nice. A very simple example is if you make the three-sphere something known as a squashed sphere. That's just a fun example. So that's a one-parameter deformation of the three-sphere that's continuously connected to the three-sphere. And the solutions, when you do that, are known, and indeed one can test the theorem of Friedrich for small enough deformations. Now, having said that, there are also theorems, I forget exactly who you can find the references to these theorems in this article over here. In that case, at the classical level, it just continues. So there exists a finite neighborhood of nonlinear, eternal, square minus, square plus. By the way, this is the first question. If anyone is interested in the stability of a de Sitter universe, this is the first question we need to address. It's the most basic question. Let aside metastable, whatever, large quantity. We should first properly understand what's known about the classical features of this system. If and only, no, not only, not necessarily, I don't know, I don't remember, but I'm not sure it's if and only if. I'm trying to cook up no, for example, the constraint on the topology, it can be relaxed, because I can take a discrete quotient of the three-sphere into something known as a length space. It turns out that there are nice smooth quotients of the three-sphere into other manifolds of different topology known as length spaces, and those evidently allow for a smooth continuation as well, right? Because all I'm doing is changing the three-sphere part of the metric with a quotient without affecting the time behavior, and none of the cycles or whatever non-trivial aspects of that topology shrink. So no, it's not if and only if. I think I've answered the question. Yeah.
Example, what happens?
Yeah, it becomes some sort of taub nut type solution, and it just re-expands into another squash sphere. It's not good news that the grad students are not asking this question. It means that this is too advanced, but okay.
Question is, so you said if you take a big enough information, you cannot extend it to...
Oh, good. So there's some condition. It was what I was about to say. So I will give you a trivial example. Let's relax the topology condition from being like spherical, and let's instead put a 3 torus on the boundary. What that amounts to is quotienting R3, and of course what it means is that at large enough eta, the proper size of the cycles of the torus become very small. And hence the geometry is simply not, it's not appropriate to describe the geometry by classical general relativity once the proper size of the torus cycle becomes too small. In effect, so it's very simple once we relax the topology condition, even with solutions that we know is sort of topological big bangs, to start creating shrinking cycles. Okay? But I was trying to remember what the general statement is, and it's escaping my mind, but I believe conditions like if the Ricci scalar is pointwise negative everywhere at scribe plus, and the topology is non-spherical, I think it's almost guaranteed to acquire a big bang singularity at some early point. Okay, but again, let me not make any statements. I have the literature, the references over here about these interesting classical GR statements. Another person another mathematician that studied this problem is Anderson. So the classical, okay, so now there's two ways to view this. Of course, I could time reverse and oh god. We can so let me just make a few last remarks before next lecture turning on a small h bar. So we can of course time reverse our discussion right now, and it's a matter of does the contracting phase always lead to a big crunch? And the answer is no, again, because sometimes it doesn't, sometimes it doesn't. But it can, okay? And so depending where your Cauchy data is, different things can happen. And so oftentimes when people talk about the analog of a no-hair theorem for de Sitter, which is that any deformation of the Cauchy data leads to a smooth structure at late times, they're making a very important assumption, which is that wherever they're taking their Cauchy data, the extrinsic curvature is positive at each point. And so they're conditioning on the fact that they're already in an expanding phase. And so the past of that Cauchy data in these cosmic no-hair theorems could, of course, be singular. And one must be careful about these statements. Okay, so I think we'll leave it at that for today. And then tomorrow we'll see how these classical features appear in the quantum description. Thank you. Any questions? Okay, let me mention another coordinate. Yeah, thank you. Thank you for that question. You gave me the time I needed. But of course that means that now you don't need to come to the third lecture. You should still come. So let me mention one more coordinate system. Let me say a funny story first and then mention the coordinate system. So this geometry was discovered a long time ago. It was one of the first solutions of general relativity. And the history of how, if I understand correctly, the history of how it was discovered is that Einstein was looking for a static universe. And he found a static universe known as the Einstein static universe, which was the product of a three-sphere times time, by balancing it with some special matter stress sensor. But it was quickly shown that this is unstable to linearized perturbations, that they grow and sort of destroy his dream. And de Sitter turned on Einstein's cosmological constant and came to him and said, I have a static universe that seems stable. And so the first discovery of this geometry was actually as a solution to de Sitter's static universe. Now, this should raise some confusion marks in your heads right now, because I've been giving you a very essentially time-dependent description of the geometry, but let's recall for a second the Penrose diagram. And I should say, what I'm about to say is not true for any FRW cosmology. This is true for the de Sitter cosmology. It's something unusual. So imagine we're sitting inside this universe, okay, and we'd like to see what piece of the universe can affect us and what piece of the universe can be affected by us. Okay, so this is a basic experimental question, because after all, physics is about that which can be observed. And so we should have really asked this question early on. But I apologized early on, and my apology wasn't good enough, so now we will describe it. So if I send a light ray in the earliest point of my existence, okay, the best I can do is affect this part of the universe. Similarly, any physics that occurs in the other half over here, classically, is out of reach, okay? So here we are, and there's an overlap between the region of physics that I can access, that an observer can access while living on a world line inside of de Sitter, and the region of physics that can be affected, okay? And so it would be interesting if there was a coordinate system that described not a half or the full de Sitter, but that particular patch of de Sitter. And the answer, which as I said was the first metric ever written down for this cosmology, takes a remarkable form. And justifies de Sitter's communication to Einstein. So So I claim that this is a solution to the theory, the classical Einstein theory of the positive cosmological constant, where the coordinate r ranges from 0 to 1. Okay? This is now the round metric on the 2 sphere, which notice shrinks at the point of the observer. Okay? This is the celestial sphere that shrinks or grows as we look out in every direction. And you will immediately note that this is an entirely static description of a rather large piece of the de Sitter universe. This is remarkable. This is a remarkable fact, because we're not accustomed, and it's not customary in cosmology, for there to be a large static description of a piece of geometry. But somehow, in this case, there is. There's no black hole singularity behind the horizon. There's no mass present. It's the dynamics of the expansion of space itself that causes the redshift factor to dampen so much that eventually light cannot reach you. So somehow the expansion of space is mimicking the contraction of space of a very heavy body. But it provokes a very important question, which is, at r equals 1, the GTT component vanishes. There's an infinite redshift surface. It's an event horizon. And so it all of a sudden provokes all sorts of questions about how we should interpret this horizon. Okay? But we'll get there we'll get there when we get there. And so it's rather nice, because both descriptions are relevant. Now, the redshift of the galaxies has to do with this observer over here. But the photons that we're observing actually have to do with an observer that exited the inflating era of the universe, so that he or she could get data that come through the late time slice. And this is why the scale invariance, eta to lambda, eta x to lambda x, is manifest in the photons of the CMB, but not in the redshift of the supernova. Okay, so that's all I'm going to say for now about the static de Sitter universe. Okay, any more questions? Thank you.